Have you ever wondered why Nvidia keeps building faster and faster AI chips, yet the biggest AI companies still complain their systems are waiting around, instead of actually computing? It turns out the biggest problem isn't always the GPU anymore. Sometimes it's what connects them. And now China says it has built an AI network that moves information so quickly it could remove one of the largest bottlenecks in modern artificial intelligence. If that's true, it changes far more than benchmark scores. It changes how future AI supercomputers are designed, how much they cost to build, and who can compete in the global AI race. Today, we're breaking down why this network matters, why Nvidia has spent years trying to solve the same problem, and why China's latest breakthrough has the entire semiconductor industry paying attention. When most people hear about AI hardware, they immediately think about GPUs. Nvidia has become almost synonymous with artificial intelligence because its graphics processors train and run many of the world's largest language models. Every headline talks about faster chips, more memory, more tensor cores, and larger AI clusters. But here's something many people don't realize. The bigger an AI system becomes, the less important the individual chip is compared to the speed at which thousands of chips communicate with each other. Imagine you own the fastest sports car in the world. It can reach incredible speeds in seconds. But then you place that car in the middle of a traffic jam where every road is clogged. Suddenly, it doesn't matter how powerful the engine is because it spends most of its time waiting. That's exactly what happens inside massive AI data centers. Thousands of incredibly powerful processors constantly need to exchange enormous amounts of information. If those connections become congested, the expensive GPUs sit idle waiting for data instead of performing calculations. That waiting time is incredibly expensive. Some of today's largest AI clusters cost hundreds of millions, sometimes even billions of dollars to build. Every second a GPU isn't fully utilized represents wasted money, wasted electricity, and slower AI development. This has become one of the biggest engineering challenges in modern computing. For years, Nvidia has been attacking this problem with technologies like NVLink and InfiniBand. These aren't GPUs themselves. They're the highways connecting those GPUs together. The faster the highway, the more efficiently every processor can work. Building these high-speed connections has become almost as important as designing the chips themselves. Now China appears determined to solve this challenge from another direction. Rather than simply building faster processors, Chinese researchers and technology companies have been investing heavily in networking technologies specifically designed for artificial intelligence workloads. Their goal isn't just faster downloads or faster internet. Their goal is dramatically reducing the time it takes for thousands of AI accelerators to exchange data while training enormous neural networks. That sounds simple until you realize just how much information modern AI systems move every second. Training a cutting-edge language model isn't like downloading a movie. Imagine thousands of processors all solving different pieces of the same giant puzzle simultaneously. After each step, every processor needs to share what it learned with thousands of others before moving to the next calculation. This exchange happens millions of times during training. If even one part of that communication slows down, the entire system becomes less efficient. That's why networking has quietly become one of the most valuable technologies in artificial intelligence. The interesting part is that networking has traditionally received far less public attention than GPUs themselves. Headlines celebrate trillion-parameter models and record-breaking chips. But the infrastructure connecting everything together usually stays behind the scenes. Yet many engineers argue these connections are becoming just as important as compute power itself. China clearly recognizes this trend. Over the last several years, enormous investments have gone into domestic networking equipment, optical communication systems, advanced switching technologies, silicon photonics research, and ultra-fast data center architectures. Instead of relying entirely on imported networking ecosystems, Chinese companies have increasingly focused on building their own complete AI infrastructure stack. That strategy mirrors what we've already seen happen across semiconductors. First came investments in domestic chip manufacturing, then memory, then advanced packaging, then AI accelerators. More recently, optical communication and photonic technologies began receiving massive attention because engineers realized future AI systems would eventually hit limits not inside processors, but between them. This is exactly where the latest reports become so interesting. Instead of asking how to make a single GPU faster, researchers are asking something much bigger. Every GPU could spend dramatically less time waiting. Even a relatively modest improvement in communication efficiency can produce surprisingly large improvements across enormous AI clusters. Think about a warehouse filled with thousands of workers. If every employee loses only 10 seconds waiting for supplies every hour, the total lost productivity becomes enormous. Now imagine eliminating most of that waiting time across an operation employing thousands of people. The overall improvement becomes much larger than those 10 seconds initially suggested. Large AI clusters behave similarly. Tiny communication improvements, repeated millions of times, can save extraordinary amounts of computation. This is why companies around the world are investing billions into networking technology. It's also why China's latest efforts have attracted international attention. Many analysts believe future AI competition won't simply revolve around who builds the fastest processor. Instead, it may depend on who builds the fastest complete system. That's a major difference. A complete AI system includes processors, memory, networking, storage, cooling, software, power management, manufacturing capability, and increasingly, optical communication. Whoever optimizes every layer gains advantages that individual component improvements alone can't match. China appears increasingly focused on this systems approach. Rather than chasing one spectacular headline after another, many recent projects fit together like pieces of a much larger strategy. You've probably noticed this pattern if you've watched several videos on this channel. First, there were domestic AI accelerators, then high-speed memory developments, then glass-based technologies, then advanced packaging, then ultra-fast optical fibers, then AI servers, then CPU breakthroughs, now networking. Individually, each story seems impressive. Together, they begin forming an ecosystem. That's important because AI isn't powered by isolated inventions anymore. It's powered by entire infrastructures. This also explains why many governments have started viewing artificial intelligence less like traditional software and more like national infrastructure. Countries aren't simply competing to build chatbots. They're competing to build entire computing ecosystems capable of supporting future industries. Healthcare, autonomous transportation, scientific research, drug discovery, manufacturing, defense applications, climate modeling, financial systems. Every one of these increasingly depends on artificial intelligence processing massive data sets at extraordinary speeds. And every one of those workloads depends on communication. The challenge becomes even greater as AI models continue growing. A decade ago, training systems containing millions of parameters seemed impressive. Today, billions have become common. Trillions are already appearing. Future systems may become even larger. As models expand, communication requirements grow dramatically. Moving that information efficiently becomes one of the defining engineering challenges of modern computing. That's why networking engineers have suddenly become some of the most valuable specialists in artificial intelligence. They're building invisible technologies that determine whether tomorrow's AI systems spend their time calculating or waiting. This is where optical communication enters the conversation. Traditional electrical connections eventually face physical limitations involving heat generation, signal degradation, and energy consumption. Optical communication offers an alternative by transmitting enormous amounts of information using light rather than conventional electrical signaling. China has invested heavily in this area. Recent announcements involving air-filled optical fibers, photonic devices, advanced optical switching, and integrated communication technologies all point toward one long-term objective: move vastly more information while consuming less energy. If successful, that combination becomes extremely attractive for AI infrastructure. Energy consumption has quietly become one of artificial intelligence's biggest challenges. Every new generation of larger AI clusters requires enormous amounts of electricity. Data centers already consume significant power. Future AI facilities may require even more. Improving communication efficiency doesn't only accelerate computation. It can also reduce wasted energy by allowing expensive processors to spend less time idle. That creates a double benefit: higher performance, lower operational cost. Those economics matter enormously. The largest technology companies now spend billions constructing AI infrastructure. Even relatively small percentage improvements can translate into hundreds of millions of dollars over time. This explains why networking technologies have become strategic assets rather than supporting components. The companies that master them may gain advantages extending far beyond raw processor performance. And according to recent developments, China clearly wants to compete at every layer of that stack. So what exactly makes this reported AI network different from the traditional approach? Instead of treating networking as an accessory to AI hardware, the latest Chinese developments suggest networking is becoming the foundation around which future AI systems are designed. The objective is simply increasing raw bandwidth. Engineers are trying to reduce latency, improve synchronization between thousands of processors, eliminate communication bottlenecks, and make every computing node behave almost like part of one enormous machine. That distinction is incredibly important. Imagine trying to coordinate 10,000 people on a project. Communication is fairly easy. Now imagine coordinating 10,000 people who all need updated information every few milliseconds. Suddenly, communication itself becomes the biggest challenge. Modern AI clusters face exactly that problem. Every training cycle requires processors to exchange parameters, gradients, weights, and intermediate calculations. As clusters grow larger, the amount of communication grows even faster than the amount of computation. That's why networking has become one of the hottest areas in semiconductor research. Several Chinese companies have already demonstrated advanced AI servers, domestic switching equipment, optical interconnect technologies, and high-speed communication platforms. While each announcement might seem unrelated, together they point toward an effort to reduce dependence on foreign AI infrastructure. This also explains why Alibaba's recent 128-chip AI server attracted so much attention. Many people focused on the processors themselves. But the more interesting question was this: how efficiently do all 128 processors communicate? The same applies to China's no GPU supercomputer projects, its photonic chip developments, and its advanced optical fiber demonstrations. These aren't isolated breakthroughs. They're pieces of a larger puzzle. If China successfully combines domestic processors, domestic memory, domestic networking, domestic packaging, and domestic manufacturing into one complete ecosystem, it becomes far less vulnerable to outside supply restrictions. That's a strategic advantage that extends well beyond artificial intelligence. It means researchers can continue building larger AI systems using technologies developed and manufactured within their own industrial ecosystem. For Nvidia, however, this creates an interesting challenge. The company remains the global leader in AI hardware, and its networking technologies are among the most advanced in the world. Nvidia doesn't simply sell GPUs anymore. It sells complete AI infrastructure, including networking, software, switches, communication libraries, and integrated systems. That's one reason Nvidia has been so successful. Customers aren't buying individual chips, they're buying an entire AI platform. China appears to be pursuing a similar strategy, but using domestic technology wherever possible. Whether that ecosystem ultimately matches Nvidia's performance remains an open question. But even approaching comparable performance would represent a significant achievement, especially considering how quickly China's AI hardware ecosystem has evolved over the past several years. Another reason this matters involves cost. Building one of today's frontier AI data centers requires staggering amounts of capital. GPUs represent only part of that expense. Networking equipment, optical transceivers, switches, storage systems, cooling infrastructure, electrical distribution, and physical construction account for enormous portions of the overall investment. If communication technologies become more efficient, companies may need fewer networking devices to achieve the same workload. If processors spend less time waiting, fewer processors may accomplish the same training task. If energy consumption drops, operational costs decrease year after year. Those savings compound across facilities containing tens of thousands of accelerators. Suddenly, communication improvements become financial improvements. That's exactly why investors closely watch networking announcements, even when they don't generate the same headlines as new processors. Now consider another trend happening simultaneously: AI inference. Training enormous models receives most of the attention, but inference, actually running AI after it's trained, is becoming an even larger market. Billions of users interacting with AI assistants, image generators, autonomous vehicles, industrial robots, medical systems, and enterprise software require enormous infrastructure. Inference also benefits from faster communication, especially when requests must travel between multiple processors and memory systems almost instantly. Future AI won't exist inside one processor. It will exist across entire distributed computing environments. That's why networking matters for both training and deployment. There's also another technology quietly entering this discussion: silicon photonics. Instead of moving information using traditional electrical signals through copper connections, silicon photonics uses light traveling through optical pathways. Light experiences lower resistance, generates less heat, and can carry tremendous amounts of information simultaneously. Several countries are investing aggressively in this technology because many engineers believe future AI data centers will increasingly rely on optical communication rather than purely electrical connections. China has been especially active here. You've already seen stories on this channel involving glass chips, photonic manufacturing, air-filled fiber, optical communication, and integrated photonic devices. Viewed separately, each seemed like a fascinating breakthrough. Viewed together, they reveal a long-term direction. Replace communication bottlenecks with light. That doesn't happen overnight. Entire industries must adapt. Manufacturing changes, software changes, data center architecture changes. But once that transition begins, the performance gains can become substantial. It's similar to the transition from hard drives to solid-state storage. At first, only premium systems adopted SSDs. Eventually, they became standard because the performance difference was simply too significant to ignore. Networking may follow a similar path. The fastest future AI systems could increasingly rely on optical communication internally. Another fascinating aspect of China's strategy is diversification. Rather than betting everything on one technology, Chinese companies appear to be exploring multiple complementary directions simultaneously. Photonics, advanced packaging, novel memory, glass substrates, three-dimensional integration, domestic AI accelerators, optical networking, ultra-fast fiber. Each technology strengthens the others. That's important because AI performance rarely depends on one breakthrough anymore. Progress happens when dozens of improvements arrive together. Think about Formula One racing. Winning doesn't come from having only the strongest engine. Teams optimize aerodynamics, suspension, tires, brakes, fuel efficiency, weight distribution, driver strategy. Tiny gains across every category produce enormous advantages on race day. Artificial intelligence infrastructure works the same way. Every percentage improvement compounds. Better networking improves GPU utilization. Better memory reduces weighting. Better packaging shortens communication distances. Better cooling allows higher sustained performance. Better software coordinates everything more efficiently. Eventually, the combined improvement becomes much larger than any single breakthrough. That's exactly why complete AI ecosystems matter. Looking ahead, analysts expect competition to become even more intense. The next generation of AI models will almost certainly require even larger computing clusters. That means networking requirements will continue growing. Data movement will become even more critical. Energy efficiency will matter even more. Infrastructure spending will likely continue breaking records. Every company wants faster AI. Every government wants technological independence. Every cloud provider wants lower operating costs. Networking sits directly in the middle of all three goals. For viewers, the biggest takeaway isn't whether one country wins tomorrow. The real takeaway is understanding where the industry is heading. For years, headlines focused almost exclusively on processors. Now the conversation is expanding. Memory matters, packaging matters, cooling matters, optics matter, networking matters, and increasingly, the companies mastering every layer of the AI stack will likely shape the future of artificial intelligence. Whether China's latest AI networking technologies ultimately outperform competing solutions remains something the industry will continue evaluating as more systems are deployed and independently tested. Performance claims always require real-world validation across diverse workloads. But regardless of exact benchmark numbers, one conclusion is becoming increasingly difficult to ignore. The global AI race is no longer only about building faster chips. It's about building faster systems, complete systems, integrated systems, entire ecosystems capable of training, deploying, and scaling artificial intelligence more efficiently than ever before. That's why announcements involving networking may soon become just as important as announcements involving GPUs themselves. The future winners won't necessarily be those with the fastest individual processor. They may be the ones whose processors spend the least amount of time waiting. And if that's the direction artificial intelligence is heading, then today's networking breakthroughs may end up being remembered as some of the most important developments of this entire AI era. Because in the next generation of AI, speed won't just be measured inside the chip, it will be measured between them. If you enjoyed today's breakdown, don't forget to like the video, subscribe to the channel, and turn on notifications, because every day we cover the biggest breakthroughs shaping China's technology race, from AI chips and memory, to photonics, robotics, semiconductors, quantum computing, and everything in between. Thanks for watching, and we'll see you in the next one.